see. Can you hear me in the back? Yes, you guys are good? Okay, excellent. Okay, let's get started. So everyone please come in and take a seat. You are the true believers. Welcome. We're going to learn some things today. Are you excited? Okay, excellent. My name is Connor Cunningham. I work for SQL Server. I'm an architect on the query processor team. I like to tell people it's my fault your query is slow, which is probably true. Not necessarily only me, but me and the people with whom I work, or I'm fortunate enough to work with. So who am I? I've been building database engines for pretty much my whole professional career, most of that at Microsoft. I spent 1 or 2 years outside the company trying to do real work and startups, and I decided that I needed to go back inside of the Microsoft machine. I had more fun there. But overall, I have a great time building database engines and coming and talking to conferences like this because I get to learn about what you guys do with the product. You have a wealth of information that we can use to make our product better. That's right. And overall, if I don't come talk to you, then we don't make as good a software. So I appreciate you coming today, and I hope to be able to interact with most of you to learn something about what you guys are seeing in the product and what kinds of things you think we should be adding to the product. Other things I've done, I wrote a chapter for a book not too long ago that's sort of similar in style to this talk, and it's about how the optimizer works. It's the SQL Server 2008 internals book. You can go get it at the bookstore if you want. I also write a blog called Conor versus SQL where I talk about pretty much whatever questions you guys send me so that anyone can learn whatever I happen to be willing to talk about publicly about how the system works. Okay, what will we do today in this talk? Every year I come up and I can give a talk on the optimizer or what works in the query processor this way or that way. So I just kind of pick a different topic. And I polled a couple of customers and asked what sorts of things they would find interesting. And one area where I didn't think people had a great pile of knowledge was how insert, update, and delete queries work underneath the hood. So I just figured, well, this time I'll do a talk on that, and people will learn things. And next time maybe I'll do a different talk. So the thing that I can tell you that most of the people who do not work at Microsoft can't tell you is why various things work the way they do, right? Because we make the choices about what the algorithm does, and I can tell you what the algorithm is and why we made that choice. And my hope today in the talk is to give you enough of a basis so that when you're looking at the next problem that you have in real life, you can say, well, why is the plan shaped the way it is? And what does that mean about what I should do when I'm debugging a problem, or why this update query is slow? And you should be able to take that and hopefully guess a little bit more intelligently next time about what you might be able to do to fix your problem using this information. I'm also going to talk about the architecture of updates. So the next time a feature comes out, you should be able to guess maybe how would it fit into the update architecture. So if you were going to go build your own updates, this probably isn't sufficient for you to cover all the details about how to build a full query processor, but it's enough for you to be able to look at a live system that you've implemented on top of SQL Server and hopefully make some educated guesses so that you can do the right thing and not waste your time when you're trying to make sure in the middle of the night that you get your problem solved and your boss doesn't yell at you the next day. So it's a deep talk. I try to make these accessible. It's not intended to scare people away, but I won't lie to you and say that the subject is easy. It takes the average new developer that we hire at least a year before they stop walking around the hallways confused on our team, and myself included. And so I won't lie to you and say that there is something that you can learn in an hour which is going to make you fully competent in the subject, but I do hope to give you enough of an overview that you'll be able to do the first couple of steps and not feel too bad about it. You have a question? No? Okay. So I won't cover everything about updates. It just doesn't fit in an hour, and people, maybe that's a different talk, but I'll talk about the subjects I will cover, and I'll answer questions at the end if there's specific things you'd want to know. And secondly, and perhaps most importantly, what I'm going to tell you, I reserve the right to change tomorrow in the query processor. So this is not something that if you call up CSS and said, Connor told you such and such, that they're going to give you the time of day. So this is all your own benefit and not something that's published in the books online, okay? So here are some of the topics we're going to cover. Basic updates and architecture, Halloween protection. Why would you want to protect against Halloween? My 4-year-old daughter asked me. You don't typically for her, but for us in databases it's very important. narrow plans and wide plans, some stuff called split sort collapse, which maybe you've seen in query operators when you look at the XML show plans, foreign key validation, how locking works and roughly how it is hooked up, index views and how they get maintained, and updating views that are not indexed. And if you want to be able to do some partitioning, how that also fits into the architecture. So you'll notice that there are a few topics that are not in here, but we also have a fairly full agenda just on this part of updates. So if there's a section on, say, cursor-based updates that you're really, really excited about, just bring it up afterwards, and I'll be happy to tell you, in the context of what we're going to learn today, what additional information you need to know how that section of the code works. But I can't really do a proper talk in an hour or two that covers all the subjects. I've tried, and I just can't do it. People get confused, including me. Okay, so I need to describe one piece of vocabulary before I go further. Inside of the query processor, we really only have one operator that does updates. We call it stream update. But it really does inserts, updates, deletes, and merge. So when I say update in this talk, I really mean insert, update, delete, and merge. But I'm really lazy, so I just want to say update, because that's what we say on the QP team. And after a while, I forget. So if I want to talk just about updates specifically, I'll say updates and only updates. But otherwise, just assume that I'm using this as a macro to refer to all of those commands. Okay, so here's how you build an update processor. It has three parts. First, you read the rows. Second, you figure out the new values. Third, you write the rows. Okay, the talk is completed. Fill out your form. Just joking. But honestly, this is the starting point. Every single update inside of SQL Server has this basic template. Now, inserts don't actually need to read the rows because they don't exist, but they do need to actually push the rows in. So they have a thing that pushes in the parameterized values that you created for the update, for the insert, excuse me. And updates will read the rows, compute the new values, and write the rows. Deletes obviously don't need to write the rows and care about what happens. It just deletes them. But effectively, the shape is the same on all of those patterns. So if you look, so as a point here, I'll post my slides so you don't have to furiously try to draw down this. I won't do live demos because I want everyone to be able to see the screenshots that I did on my computer, and I will zoom it up so you guys can see it in the back. But overall, you should be able to see every example here and try it on your existing copies of SQL Server. Some of the things will be 2008 and onward specific, but you can try all the examples even on 2005 if you're still running that. So let's take a look down here at what this is. If I were to create a table, basic, and it has a column, it's a primary key, and I insert a row into it, and then I create an index, which is a secondary non-clustered index on basic, same column. So now I have two indexes on this, and I update it with a where clause. The basic pattern is going to be the seek, which is the read, the top, which you should ignore, the compute scalars, which is where we compute the new values. Why do we have two compute scalars? Because we were lazy. We didn't fix it to have one. You'll see later where we actually are even worse. I need to go talk to a couple of the guys in the team. When I was presenting this, I'm like, 4 compute scalars in a row? This is crazy. And then update, and that's the pattern. So this is the simplest form of update, and you can see this anytime you go look at a query, right? Nothing's too fancy here. Once you have this pattern, you need to understand what deviates from this pattern. So if you see an update query and it doesn't quite follow your pattern, start from it should look like this, and then work your way forward. Okay, so I want to talk a little bit about the architecture of how the internal code works, because some of the things that happen in the QP are based on what happens in the storage engine. So inside of SQL Server, there's a section that does queries, and there's a section below it which does storage engines and transactions and locks. And so the query processor component will talk to the storage engine component at different times. And every time that you're doing a table scan or a seek and you're getting a row out of the storage engine, what really happens is logically the following. First of all, the query processor has an operator, which will be a get, which will be a scan or a seek, and it'll actually go down to the storage engine and say, give me a row. The storage engine will say, well, I need to lock that resource, so it goes off to the lock manager and asks for a lock on that, which usually is a row, but it could be a table or a page. And then it returns back that it acquired the lock, or it blocks until it does acquire the lock. Then the storage engine says, great, I want to get that page now. And so it goes and reads the page off the disk because no one else is using it, or at least is not using it in a compatible manner. And they make sure that it's in the buffer pool. Then the page gets read in the buffer pool, and the row from that page gets returned back up to the query processor. And then whatever the query processor was going to do goes on its business. In our case, in the previous example, we would go compute the new value and then go back and try to write that value. But in any select query, the same basic rules apply. It's just how we lock is a little different in the update case. So the piece that I want you to take away from this is that the query processor plan doesn't directly control locks. Locks are sort of implicit in whatever operation the query processor happens to be executing. The locks are done by the storage engine. So if you don't ever go touch the storage engine to read a row, you pretty much don't lock the row. You also don't see anything inside the XML show plan that directly tells you when a lock is acquired and when a lock is released, because it just happens as a side effect of the operators that are there. So far, so good? Oh, the other piece of information that you want to know, and this will come up later, is that uniqueness, such as unique indexes, is actually enforced by the storage engine as well. So when you're writing to an index to, say, insert a value into it, and you get a unique key violation, the QP is not doing that for you. The storage engine is doing that for you. And that'll come up soon in ways that you probably never knew that you had to care about in building a database engine. And one of the examples, it'll be a slide or two later. Okay, I've given various forms of talks on how the optimizer works. And one thing that has come up again and again that I think is important for people to understand and probably isn't obvious looking at anything that SQL Server tells you in its books online is how indexes are actually put together. Because if you don't know how they're put together, it's pretty hard to understand how you're going to update all of them. So SQL Server supports heaps and clustered indexes, right? People probably are aware of that part. And you can also have secondary indexes, which are really just copies of portions of the data. So you can really have, if you created a secondary index that was all of the columns, you would actually have 2 copies of the table. And it would take twice the storage. Now, that's the basic part. After that, it gets a little bit trickier. Because you can actually have a row in the secondary index, or the non-clustered index, and you need to go find that in the clustered index. That's what a fetch or a bookmark lookup can do. But how does it do that, right? What do we do to make sure those things are linked up? Because you can have non-unique indexes, and those values could just be random values, and you have no idea how to tie those two together. How does SQL Server track what is a row in the clustered index, and what's the same row in the non-clustered index? Tell me, Connor, how does it work? Well, the way it works is that we actually add magic columns to keep track of it. And it boils down to a couple of different cases. If you have a heap is just a collection of pages, and they don't really have any hierarchy structure. You can scan through them, and you can go look at things in the heap. The heap can be addressed by a bookmark, which is really effectively a physical locator. What's the page offset in the file, effectively? And that is called a RID, or a bookmark, and it's 8 bytes in SQL Server. It doesn't have to be 8 bytes. We just happen to support 8-byte bookmarks in this particular product. And it has been that way since SQL 7. Other products probably also have 8-byte bookmarks, but they don't have to. They can have different kinds of bookmarks. But effectively, a bookmark is just a physical locator. So whenever you have a secondary or non-clustered index created against a heap, what we actually do is we'll put the record locator of that heap inside the secondary index as an extra column. And that way, whenever you go and look things up in that index, that secondary index, we can actually always go back and find the original value in the heap. If you have a clustered index, the same concept applies, except there's 2 cases. If I have a unique clustered index, I don't actually need a physical locator, because the fact that I have a unique index means I can always find a unique value for my row. And so in the secondary index, the non-clustered index, I'm sorry, I used to work on Access, and the term that we use there is secondary index, so I apologize. I always jump back to that. When I say secondary index, I mean non-clustered index in SQL Server speak. Whenever I have a unique clustered index, I actually will store whatever the clustering key is inside that non-clustered index. So if you created an index that was just 1 column, it'll add whatever number of columns that were in your unique index to that. And that's just implicit. You can't control it. And that goes and counts against your 900-byte width length. It's still 900 bytes, right? We haven't changed that. Okay. So if the index is non-unique, the clustered index is non-unique, it's actually trickier, because now I have no unique way of identifying and tying those 2 indexes together. So we add a special column on the clustered index when it is non-unique. And because we were really creative, we called it a uniqueifier. Exciting names, yes. Imagine talking to people in the hallway in Building 35 in Redmond, and it's acronyms and weird names like this all day. So a uniqueifier is basically just a random number that we create. It's not random, it's unique. So it's just like an identity column where we make it unique for you. And we'll put that into the clustered index and into the second non-clustered indexes. So just like you're adding extra columns implicitly for the unique case, you're adding another column in the non-unique case. So if you can make your clustered indexes unique, it might make your secondary indexes incrementally smaller. Now, you can look at this today. It's not obvious when you're playing with SQL Server, but there's a couple of DMVs, sys.system, internals, partitions, and partition columns. And you can actually go see here. In this case, I created a regular table, and I created a clustered index on that table on call 1, and I created a non-clustered index on call 2. So this is the non-unique clustered index case. In the non-unique clustered index case, if we go down and look, instead of having just one column in my secondary index, I actually have 3. So down at the bottom, index ID 2, there's the first column, which is the one that you wanted. Then there's the second column, which was the clustered index key, which was a single column index. And then there's the third column, which was the uniqueifier. So now you have a pretty good idea how we're going to be able to find rows. If you go update a table, how do we find all the rows in the secondary indexes, non-clustered indexes? It's too early for me to be giving a talk, obviously. This is the way we hook it up. So all update operations will leverage this requirement on any secondary structure. Yes, sorry, I didn't see you.
What's the storage size on the uniqueifier?
Uniqueifier, what's the storage size on the uniqueifier? Uniqueifier is a 4-byte value, and so every single row would be 4 bytes. Bookmarks are 8 bytes. Now, funnily enough, you'd think 4 bytes could actually store 2 to the 32, which is approximately 4 billion, but the total number of uniqueifiers is only 2 billion. And for why, you have to come to my talk tomorrow that I'm doing with Boris. So I have a demo, an example that I debugged earlier this year on exactly that problem. So uniqueifiers are just 4 bytes, and they won't make or break your total 900-byte limit, but just be aware that they're there. So just a second. There's a question in the back. I'm sorry, can you? Is the uniqueifier stored if it is not 0? All uniqueifiers are stored. If there's a uniqueifier, as of this DMV, then there will be storage acquired for that in every single row that you have on that access method. Yeah, so it doesn't have anything to do with whether it's 0 or not. It may be that the uniqueifier itself has a function that you can go access it, and if it's not there, it might return 0. But it's based on the schema choice, not whether it's 0 or not. So if you have a non-unique index, you will have a uniqueifier, and then it would be stored in all cases. Yes?
Even though it's considered integer type, I mean, it's going to the left of that row, it will be 53, the type of the column type of the unifier, but it's still stored in the variable part of the index page. Why is that?
So the question is, why is it stored in the variable part of the index page? I don't know. No, they can't grow. You can run out of uniqueifiers. I can assure you. You'll find out tomorrow that you can run out of uniqueifiers. So it's not because it's set up to grow. It might just be that it was a design choice by the person implementing it. It doesn't have any functional issue associated with that, to my knowledge, right now. Okay.
I think the uniqueifier isn't unique by itself, but along with the cluster key.
Yes, so I'll clarify. Uniqueifier helps make whatever the existing key is unique. It's not completely unique for the whole table. Okay, let's keep going. Halloween protection. So let's talk about why you need Halloween protection. Long time ago, when they were first building database engines, they wrote a particular query and tried it out, and they had a problem. And the problem was they were trying to give everyone a 10% raise who had a salary less than a certain amount. And all of a sudden, they found that it went into an infinite loop and never returned. And fundamentally, what's happened was that when you're reading the value from a secondary non-clustered index and then you update it, you're actually deleting it and moving it And if you're scanning an index in order, and you happen to be increasing the value that makes it go into that index, you can actually see the same row more than once. This is the point of the talk when people's brains start to ooze out of their nose a little bit. But fundamentally, it's going to get worse, so welcome to my job. So Halloween protection is effectively, what do you do when you actually have a problem like this, right? Your database engine just goes in a loop, and you don't want to give people, well, I mean, if it's you who gets more than a 10% raise, that's great, but if you're the boss, you're going to be really upset about that. So overall, the expectation is that you don't give anyone an increase in their salary more than once. But for this particular query on this particular day, for that particular query plan, it happened to be that you could get the thing to go and update the same row multiple times. So let's talk about why. When you're reading rows and computing the new values, there's no requirement that you actually see the rows only once, right? If you have a physical structure and you move a row from one place to another in that physical structure and you go to the next page and that row is there again, well, that's databases for you. The work that SQL Server provides for you is to figure out how to make sure that those kinds of problems don't happen. So any commercial system will have to have some form of what's called phase separation, which is making sure that you don't have the problem of seeing a row more than once. Some people call it ghosts, where you see the ghost of the record before, but I don't actually think that's part of the original description. I think that is urban lore that's been added since then. So phase separation is enforced by spooling, where you read all the rows that you're going to update, put them somewhere, not the structure that you're scanning and updating, and then you figure out the new values, and then you go update the structures. And this way, you have a clean separation between what are the set of rows I want to change and what are the actual changes I'm making. So let's look here for an example. This is the exact same query. I just created my own. Now, the only thing that I had to do here was I had to create a whole bunch of rows for Sue just to make sure that the plan choice was right. So by default, the optimizer might just pick a table scan, and that may or may not have this problem. So depending on the query plan choice, you can have Halloween protection problems or not. So here, if I have an index on, in this case, the only one that matters is the second one, index 2 on salary table, which is salary name. And the query we run is update salary table, set salary equals salary times 1.1, where salary less than 25,000. Now let's go look here at the query plan. You'll see here we have an index seek on I2, which is on the salary. So we're updating, we're using as a source of rows the table that has the value that we're changing, right? So we're increasing the salary, and we're using the salary index to figure out what rows we want. And then you'll see the 4 compute scalars in a row, because we obviously have a little bit more work to do in the optimizer to make that look nice from a supportability standpoint, and then we update. And the thing that we added here is this phase separation, which is a table spool. And that means that you read all the qualifying rows, everyone who has a salary less than 25,000, put it in a special work table, and then after you're done figuring that whole set out, go compute their new values and then write them back. And that way you never have a chance of seeing the same row more than once. So now you know why a spool is in your update plan. Yeah? Okay, so now let's do the advanced topics. So if I have an empty table, the plan that got picked was a scan of the heap, not a scan of or seek on the index. And it didn't have a spool. Why? Anyone know why? If you're scanning a heap, you're not going to move a record forward. There's no B tree, so you're not actually moving the record in the scan order. So if you scan, as long as you don't have to move a row because it got too big, you're not going to see the same row again. So the way the storage engine works in SQL Server, we have the property defined so that if you're just scanning a heap, you actually will see all the pages in order. And if you just update a row on that page, you're not going to see it again, even if you increase the salary. So it's specific to the indexing, and that's why this problem happens. There's a question in the back?
What if you do make the row bigger or change the null or not, and it gets forwarded?
Right. So the question is, what happens if it actually did get bigger? Well, you have to make sure that you talk to your storage engine team and make sure that they don't put things in a place where you're going to see it again. So we actually have guarantees about whether or not we see the same rows more than once in a scan of a heap. There's another question. Is it a spool table? Is it stored in TempDB? There are a lot of different varieties of spools. some of which are stored in memory, some of which are stored in tempdb, and on partition tables or spools that can be stored in your actual local file groups because the partition tables are so big. It depends on the case, right? So there's not one single answer to your question. I believe that in this case, it will be stored in memory first and pooled to tempdb if it's too big. Yes, sir.
Is that not what a forwarding pointer is for?
So, right. So the question is, what is a forwarding pointer for, and can that solve this problem? And the answer is yes. You could build your storage engine to have forwarding pointers to avoid the problem of seeing the same row twice, even if you did have to do a page split. And I'm not going to talk about whether or not that's the reason for this here today, because it's more about storage engine internals than update properties. So with respect to updates, yes, there are ways that storage engines can provide no need for phase separation on update queries when you're scanning a heap. Yes, sir.
Does the table spool contain only the part of the key, part of the row which identifies the row, like the unique?
What columns are included in the table spool? Is that your question? Typically, the query processor in SQL Server will figure out the subset of columns that are needed for all the operators above it to complete their job. In this case, you would need the set of columns that need to be updated, and it figures out the subset of indexes potentially that need to be changed. So there's a pruning that happens there, and it will need the index key, which will be a bookmark or a set of clustered index columns or whatever in general. Yes, sir.
Does it allocate RAM for the spool table based on row estimate? And then the question is, if the row estimate is really bad, do you have one of those issues where then it has to overflow?
How does memory get allocated for the spool operator? And can it have problems if there's bad cardinality estimates? It allocates memory for the spool operator based on cardinality estimates. If the cardinality estimates are bad, then there can be trouble. We tend to overestimate the amount of memory we need to make sure that we account for some variance in cardinality estimates versus actual. But there can be cases where you overuse the memory that you have. And today in SQL Server, that would result in spilling to tempdb. And that can be a little bit slower than obviously not doing that. But typically for this particular example, it would not be a problem. It really is only a major issue in large queries where you have memory grants, and those would typically be parallel queries. But it could be that you have enough memory that you have to wait to run this query because you don't have it in the system, or if your estimate's wrong, that you overuse the memory grant that we do give you. So to make sure everyone has the same understanding, SQL Server doesn't just let you start running and allocating memory however you want, because anyone can come up and use the system, and a whole bunch of people could do it at the same time. You could have a spike in load, and then all the queries would fail. So we have a reservation system for memory, and that reservation system is based on the estimates that the query processor uses when figuring out approximately how many rows and how wide the rows are for each of these operators in the query plan. Some operators need more memory than others. Some, like compute scalar, really don't need any memory at all because they don't have any long-lived state. But spools do have long-lived state because they have to write something out somewhere, and that could potentially be a very large amount of data. Okay, so I asked the first question, which was why do we not have handling protection on the heap case? Now for the next question. When I add enough rows, why do I get this plan instead of the heap plan?
In other words, why do you process the index rather than?
Right, why would we pick the seek instead of the scan?
Because the index, first of all, there's smaller pages in the index, so there's less stuff to look for. And actually, I don't know why it's C, but.
Right, so you actually got really close. The basic question is the optimizer will pick different plans based on how many rows you're updating. And in this particular case, in select queries, there's a common knowledge that you can have a seek or a scan based on how many rows you're selecting. And what it basically boils down to is random IOs are expensive because you have to move the disk head, right, and wait for the rotation of the media to go around. And that's the slowest thing you can do against a regular hard drive. But if you have a sequential scan, that's relatively fast. However, there's a trade-off where at some point doing the seeks, if you have a small number of seeks, is really, really fast. But if you're doing a scan, then you're better off because you have more sequential I/O than random I/O. So in this particular case, the only difference is that the seek case, which is the fast case for small numbers of changes, is actually not the most efficient because of the spool for the smallest number of records. So there's a trade-off point where if you scan the heap for 1 or 2 pages, it's the fastest plan because you don't have to spool those rows. And as soon as you have enough rows where spooling now becomes very expensive, because it's actually even more expensive than just reading with random I/O, then it switches over to the seek plan. So understanding the relative cost of these operators will tell you why you're getting one plan or another. And more importantly, why when you're testing, you should make sure to add some good sample data that represents your real workload. Okay, so you're getting better. I've got now for the advanced, oh, I'm sorry, excuse me, I didn't see your hand. Ask away.
Does the spool come into picture only if you have an index on the column that you're updating?
Does the spool is specific to the particular query plan that gets picked. And so depending on which plan gets picked, some plans don't need spools and other plans do. And it depends on a lot of things. And there's actually a whole lot of very detailed rules about when we actually have to add phase separation and when we don't. So there's not one simple explanation to your question as to why is it there all the time. But I will tell you that if you are updating the index that you're scanning and you can move the row, then there will be a spool. That's the simple rule. But there are more crazy questions, like if you're only updating one row, and we know that, and we have a plan that takes advantage of that, then maybe it's magical and we don't have to actually have the spool. So we want your plans to be fast, and we have people who spend all day dreaming up how to not have that spool there. I can assure you, that's what we do. The spool actually is, so let's be careful. So when we talk about random and sequential I/O, the optimizer has a costing model where it uses to pick one plan or another. There's a cost to spool records. It actually is just a different cost than the cost of random I/O or the cost of sequential I/O, because writing means you also have to log it in some cases, right? So when we cost the spool, it has a very high cost, typically, compared to other operations that are just reads. Because if you're going to write, you basically have to read and then write, so it's always going to be more expensive. So the only point I was trying to make is that the number of rows you have in this table or the number of pages you have will determine what kind of query plan you pick. So if you're playing with this example at home, try different numbers of rows and see what happens in terms of the plan choice. And you'll find that initially, for an empty table, you'll get a heap scan. And as you add more rows, you'll eventually switch over to the seek because the cost of doing the scan is relatively low, but the cost of doing the scan plus writing all those rows to the index spool, to the table spool, excuse me, is expensive. And so there's a cost at which spooling all the records becomes more expensive than doing the random I/O for the seeks. Yes, last question, and then we'll go on.
Is the storage engine actually handling the maintenance of the index in some way? Because I don't see it frequently, I'm not sure.
Is the storage engine doing the maintenance of the secondary, or the non-clustered index? Is that your question?
Yeah, I'm used to
Right.
seeing, like an operator say index.
Okay. So we have two indexes in this case. How come there's only one update operator? And the reason is that the actual table update is updating both the table and the secondary indexes. And I'll show you an example of that in a couple slides. So here's the hard question. So how many people know what read committed snapshot isolation is? Do I need the spools when I have read committed snapshot isolation? So read committed snapshot isolation will give you a view of the table at the start of the point of the transaction or the statement, depending on which mode you started up in. And that is very interesting because if I'm only reading rows in an index at the point that I started the transaction, I could potentially ignore my own changes to that. And therefore, I wouldn't necessarily need to spool. Now, physically, the storage engine is actually spooling each individual record that gets changed by a different transaction. It's a different concurrency model, so it actually has different rules. But we still generate the plan just like this today. And the reason is that in all the other isolation modes, you can change them without invalidating the query plan. And today, read committed snapshot isolation is the only one where this property could be true. And so we actually just keep generating the plan the way we do now. In the future, perhaps we don't have to. Now, the one thing that you might not know is in order to commit the transaction in read committed snapshot isolation, you also have to keep track of all the things that you changed and validate it against whether or not someone else changed something. Because the way that all the locking and works is that when the transaction commits is when those primary keys have to be enforced and unique constraints have to be enforced and foreign keys have to be enforced. So it's actually a head bender. It took me months to get really to the point I felt that I liked that subject. And now I want the whole thing to be read committed snapshot isolation. Okay, let's keep going. Narrow plans and wide plans. So all the plans we've seen so far are narrow, meaning that there's just one path through. You start at the end, and you go and you do the update, and then you're done. And we actually will, for each single row that we see in that pipeline, go and update all the indexes. There's a trade-off point where eventually, if you update enough rows, it makes more sense to actually update each index at a time. And this takes advantage of that difference between random I/O and sequential I/O for writes in this case. So if I'm doing a narrow update plan, every single row will update the clustered index or base table, and then every single non-clustered index, which basically is a seek for each one of those. That's slow at some point. So if you are updating a substantial fraction of the table, SQL Server's Optimizer will flip over and use a wide plan, where it'll take and all the rows, spool them, sort them in the order of the index that it wants to update, and then go apply all those changes using a scan of that index. Because then the sequential cost is faster than the random cost. Now, this isn't a perfectly orthogonal feature. Some things only work with wide update plans in SQL Server. So if you go and add an indexed view to your table, then you will always use a wide update plan to update that table. It's not strictly required, but that's the way it was implemented, and it hasn't been made orthogonal in the years since. So be aware that there are some features that we will always use wide update plans, even when we could use a narrow if we were to go do additional development work. See, giving Adam more things to complain about later when he wants to come and pester me about the next feature he needs for whatever his high-end engagement is. Okay, so you had a question earlier about how do we know what indexes are being modified in a particular update operator. So this is a narrow plan, and we have multiple indexes. So in this case, you can go look at the properties in Management Studio, and you can see what are the objects being updated. And you'll see table 1, table 1.I1, .I2, and .I3. In every single case, even in the wide case, you actually can have multiple indexes that have the same sort order. Although one might wonder why you would do this, it is legal. And therefore, you can go look and see the list of the indexes that are there that are updated. And if you have cases where an index isn't being updated, then it might not be changed. So there could be a case where we can determine that we don't need to actually update that index. You're just updating a non-key column, then we won't update the index. Okay. Sorry, go ahead.
Are you going to address partitioning and index filtering at any point in this?
At the end, I have a slide or two on partitioned tables and how they fit in this framework. Filtered indexes I don't have time to cover, but they will follow from the stuff you're going to learn here in a bit. So pay attention and then come talk to me at the end, and I'll tell you the one little tiny bit that's missing. Okay, so wide updates. So here is an example of a wide update plan. And the main point here is to show a couple of different operators that you haven't seen yet so far in the talk. Just like before, we have a table scan, or we read the rows, and then we compute the new values, and there's 4 compute scalars there, and I cut them all out so that it wouldn't look as bad. Then we have a table update. So that's the regular part that we talked about at the beginning of the talk. And now we're going to get to the advanced topics. There's a couple of things here you haven't seen before. One of them is the split operator. One is the table spool. One is the sequence. And then this other branch down here. So the first thing I want to explain to you is the table spool. We call these common sub-expression spools. Every single thing in SQL Server is a tree in terms of how the query plan looks, except for common sub-expression spools. The major place we use common sub-expression spools is in updates. And what that really means is we write to the spool once, and we can actually read from it multiple times. So the spool that's circled over there is exactly the same spool that's down here. It's just in the top phase, we're writing to it, and in subsequent phases, we're reading from it. So once you get your head wrapped around the fact that it's actually a graph and not a tree, that's the first challenge. So you're just storing them off in a workplace and then coming back to get them later. The next thing you have to understand is what a sequence operator is. And sequences are a special internal operator that says, do this branch first, give me all the rows from there, and keep in mind that we're doing updates, so it's really do all the updates in this branch first, and then when you're done spooling all those rows, let's go to the next branch, read that branch, and start updating the next index. And we'll keep doing that for every single branch we have. So a sequence does things in sequence. We're very creative with the names, I told you. So the next thing that you'll see is the split and then this sort and collapse on the bottom. And these I will have a special slide on, but just be aware that they're part of the logic that gets things sorted in the right order and does a few extra things for us as well. We've covered everything here. Okay, split, sort, collapse. Everyone still with me? You guys are excited about split, sort, collapse? Yeah. I'm excited about split, sort, collapse, I can assure you. This is another one of these cases where you didn't know that you had a problem and that SQL Server solved it for you until you came to the talk today. So just like Halloween protection, and you're like, why would you ever need that? Well, that's why you buy the product. This is another one of those cases where you didn't know you had a problem, and I'm going to tell you about it now, and you're going to be really happy that the optimizer team is there for you. So if you have a unique index or a primary key, and you have, let's just say it's an int column, and you put in the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you run the query update that table, set that column equals column plus 1. Now, if you go back and look at those query plans, you would have a read the rows, compute the new value, write the rows. Pardon me. And we would go compute that new value. So we'd read the first row, which would be 1. We update it to 2, and we try to write it back into the storage engine, and what happens? You have a duplicate key violation. This sucks. Customers don't like that. So it's called a phantom primary key violation, because if we actually completed the whole transaction, all of those rows would be legal. But in this particular case, it's not, because if you don't do something special, you would just try to write it in and do it in a per row basis instead of a per transaction basis. So how do we make that work? Well, one way would be to delete all the rows first and then write them all back in. And that would sort of be similar to that phase separation concept that I described earlier. But we actually have something that's a little bit fancier because we wanted to do fancier stuff one day, and we came up with something called split, sort, collapse. And split, sort, collapse will figure out how to determine what's the net change to each index and avoid phantom duplicate key violations. So here's an example for this particular case. We would start on the left-hand side with an update, and the way that you should look at it is update from 1 to 2, and update from 2 to 3, update from 3 to 4, etc. And that would be the stream of commands that are coming through the query tree. Each row is one of those lines. We would convert that in split to split out deletes and inserts from an update, because an update is equivalent to a delete and then an insert. So we split it out, and now we have delete, insert, delete, insert, delete, insert. Right? That seems pretty good, but it still has the wrong behavior, because if you just executed that stream physically, it would still have the duplicate key violation. Now we sort that list and determine things in the order that we need to avoid the duplicate key violation. So you'll notice the subtle change on the sort, where we're sorting by the action, which is whether it's a delete or an insert, and the key value. And we have deletes sorting before inserts. And then we collapse, where we take all those guys and determine which ones were just deletes, because we were just deleting a value, and which ones were updates, where we're going to update a value to itself. Why do we have to update a value to itself? No? No? Because no, if we were lazy, that's one good answer. Actually, I was really upset when I was doing the presentation preparation, because I was thinking that we have all this special logic I figured that it would just get rid of the rows that were the same and just delete one row at the end and add one row at the other end. But that's not what happens, because who takes the locks? Storage engine. So if you don't lock the row, then some other transaction can come in and stomp on that row. So we have to lock the row, even though we're not changing it at all, just to make sure that the transaction successfully completes. So that's why the update is there, to update a value to itself. You guys are learning all sorts of stuff today, aren't you? Let's talk about referential integrity. How many people know what a foreign key is? This is good. No, don't laugh. Honestly, I've gone to talks where people don't know. Okay, a foreign key keeps track of whether or not you have a row in one table that references a row in another table. So you have customers and orders. You don't want an order that doesn't refer to a customer, right? All orders belong to at least to one customer and only one customer. And that's enforced in the system by a foreign key. Well, how does that get enforced? Updates. Updates are the thing that make all this work for you. So we have unique indexes on one side, and we also have logic that has to go double check that that row is there if you go change it. So if you were to update the customer ID on your order table for a particular row, How do we go check that? And you take the same pattern that you've seen before. Sorry, you read the rows, you compute the new values, you write the rows, and then we have this new thing on the top that you haven't seen before. We have what's called a nested loops left semi-join, which goes and looks into the other table, in this case the primary key side or the customer side in the example that I gave you verbally. And then we have this weird operator called an assert, which for those of you who program in any procedural language will go and actually just abort the transaction if some condition is not true. So we'll try to do all these operations and validate that if you were going to go change the customer ID, that customer ID exists. And if it doesn't exist, error. Now, the next thing that you're going to notice here, I'll take questions in just a minute. I want to finish the thought. What's happening above that update? I mean, what does it mean? Like, we just updated the row. Is it still flowing rows? Yes. So all the new values are now available above that update operator. So theoretically, I could go string a whole bunch of those updates together and update a whole bunch of tables if I wanted to. Now, we don't have a legal syntax for doing that, but conceptually, it's possible to build that here because the infrastructure allows for that. In this particular case, we use that infrastructure to validate foreign keys because we take the after values and validate if the after values exist in the other table. Mine's still oozing out of your nose a little bit, yeah? So if you have the operation that's with outputs, you guys familiar with outputs on updates? Now you know why it works. Because all that an update is a side-affecting operation in the query algebra. Okay, you had a question?
If my update statement is join, when I join to the foreign key table, and I say set column equal to from the value from the foreign key table, can I skip the post check?
So the question is, if I'm updating a view,
No, my update statement is a join. If the table I'm updating joins to the foreign key table to get the value, then it should know
So,
I'm getting a legitimate
okay.
value.
You're using the non-ANSI from clause? Or you're using the non-ANSI from clause, or are you updating a view? Or a constant table expression?
So he's updating the table.
I'm updating a table.
He's doing a join.
To reference back to the foreign key.
Instead of people doing.
So how are you referencing the join? Where does that come from? Because ANSI syntax doesn't have join in update, right? You can use subqueries, where exists, where in, things like that. Or you can use the non-ANSI from clause. Or you can update a view target, which is not necessarily indexed. So you have to pick. I can answer the question, but it depends on which one you want.
Okay, I think it was the middle one. Right.
The non-ANSI from clause. The non-ANSI from clause. So the question is, if I'm trying to do logic with the non-ANSI from clause and update a join, do I have to do the validation afterwards? I don't know. I would have to go look it up. I would assume that we still add the foreign key validation logic because it's
I'm thinking it could be skipped.
right. So if I had my way, the non-ANSI from clause would be removed from the product, and we would turn it into ANSI compatible ways because there actually are some very old, odd, semantic, crusty things that happen with non-ANSI from clause updates that are very, very weird. And we can talk about those later, but I don't want to derail the talk. But overall, there is a thing in SQL Server that was inherited from Sybase called the non-ANSI from clause. So usually you would do update t from, or update from t, and there's a second from clause, which is this non-ANSI clause where you can put a whole select block in there. And that's great, sounds wonderful, except it wasn't implemented properly. And now for backwards compatibility, we have to maintain it exactly as it is, or else we violate things. And depending on exactly how you alias that, then you get different semantics. You have to be very, very careful with that. Okay. Was there another question?
Untrusted foreign keys. How does it affect? Untrusted foreign keys.
Rosent,
If the foreign key is untrusted, does it affect it?
is the foreign key is a roset?
Untrusted.
It's not trusted. Oh, what do we do about non-trusted foreign keys? We don't enforce them. So there you go. The reason why they're not trusted is that they're not enforced. So we just don't bother with them. We consider them to be not there. And when you turn them back on, we revalidate the whole foreign key. Okay, locking. So I'm going to show you just the bare essentials about how to go look at locking. I've shown you how each operator affects what happens in the storage engine, and because we know the storage engine does the locking, we want to make sure that we see where the locks get taken. Here's how you can go figure out what locks get taken. And I'm not going to give a talk on locking because it's a whole longer thing, but I do want you to know what's happening. So every time you look at a query and you're like, why am I getting a deadlock? Well, you can see. We have the same pattern here, scan, compute, write. And the thing that happens is, inside of the locking infrastructure, there's a couple of key concepts you need to understand. When you're just scanning a table, the typical lock type that we take is an S lock, which is a shared lock. It means multiple people can take the same shared lock, and that's great. So you can have lots of select queries reading the same row. When you do an update, you have to convert that lock to an exclusive lock, which means only one person can read or write that row. Now, in update queries, if I were to have two people running this exact same query at the same time, let's think about what would happen. Person number one would read and get an S lock on the table scan. Person number two, if they came in right then, would read and get an S lock on the table scan for that row. And then they both go compute the new value. Let's just say they're doing update T, set column equals column plus 1. And they both go try to write that row. And when they get to the update, it tries to upgrade that lock from a shared lock to an exclusive lock. And both of them deadlock each other because neither one can get an exclusive lock because the other has a shared lock. Now you know these are deadlocks, right? So we have a couple of heuristics inside a SQL Server update plan generation to avoid the most common cases of deadlocks, one of which is multiple people running the same query at the same time. And the way that we do that is we don't actually take an S lock on the scan. We take what's called a U lock. And the U lock is just a special lock that's compatible with S locks but not compatible with other U locks. And that'll prevent two people running this exact same query and getting a deadlock. And it's really just a heuristic more than a requirement. It's how many times do we see deadlocks. So let's look at how we actually go see. There's a DMV called sys.dmtrendlocks. And I'm not a storage engine expert, so I'm not going to give you a big long lecture on how they work. I find them to be obtuse and kind of crazy because they only give you these crazy numbers. And I don't like big numbers. I'm too old for that. But you can see the type of lock, whether it's locked, whether it's granted or whether it's waiting, what the resource is. So if you go figure out if you're looking for a page or a RID or an object, you can go track that down. So when you have the next deadlock, I challenge you, go look at this information, see if you can figure out what happened based on the plan shape and the locking behavior. And the one last thing I'll tell you is the way that I was able to see all of this was I started a user transaction but didn't commit it. So I did begin transaction, ran an update query. The locks are all still being held because the transaction's open. So that's how you can track it down manually. Oops. PowerPoint, my friend, you have failed me for the last time. Okay, now, in case any of you are still awake, we're going to talk about index view delta algebras. So what is an index view? People know what index views are? Yes? Index views are queries where the results of the queries are stored in a clustered index just like a regular table. And SQL Server somehow figures out whenever you update the table to go figure out how to keep that query result correct transactionally, right? If that didn't hurt your head, this part will. So we take the original graph from the view definition and we convert it into another view. That's called the delta view, where we take the change to the table and apply it. Instead of having the actual table be part of the view definition, we take the change of the table to the view definition and start shoving that through the view. And then we go modify each operator in the view to figure out, given just the change, how can we figure out what the change in the result of the query should be? And I'm going to show you an example, and you can go play with this and you can see how this happens. There's all sorts of restrictions on index views, and most of the reasons are to make sure that this property still holds. So in this particular case, we take a nice little group by query and we convert it into this big old nasty split sort collapse thing that you guys pay us to do. You're welcome again. Joking. So here's the example. So we're going to create a table, and we're going to create a view on that table. And there's a couple of restrictions with schema binding, things like that. In this case, it's a sum query, and we have to add count star. It's one of the restrictions for index views. And we group by call 3. So we're summing on call 2, group by on call 3. So now let's look at our query plan, because we're all experts at this now. I'm only doing the second branch in the query plan for space. So the original part where we update the original table, you guys have seen that enough times. I'm not going to show it to you again. So we read from the common sub-expression spool. We sort in the order of the index, which in this case happens to be an index view. We do the aggregate. And the aggregate's a different aggregate than the one you would have had in the original view definition. And then we go look up what rows exist or don't exist in the original index view. So down at the bottom, you see that's the materialized view. at the bottom, and we compute the result and eventually sort, collapse, and update it. So let's look at what that means. So down here in the delta view, we are trying to, whoa. Okay, apparently PowerPoint hasn't failed me for the last time. Sorry about that. Hope you all were sitting down. Okay, so here, remember how I talked about inserts, updates, deletes all go through the same operator. And there's a magic column that we call the action column. And if you go look in the plan, you see this, case when act 1019, that's the action column. And the numbers to tell whether it's an insert, update, delete, etc. So in 3 is update. No, delete is 3, update is 1, insert is 4. Not documented. But overall, we go perform that change. And what we're actually doing here is saying, if I have a result of a group by query, a sum, so let's say I had 123, and I go delete a row that had a value of 5. What I need to do to get the view right is to subtract 5 from 123. So all this logic is doing is figuring out, given 123, I want to figure out all the changes to that, sum that up, now I have minus 5. And then I go apply minus 5. So I pull up 123, subtract 5 from it, and then write that value back. And that's this example and how it works. And you can see all the logic that does that if you decide that you were really excited and going and spending your afternoon looking at how delta algebras work. There are all sorts of creative things we can do to incrementally maintain index views, and now you know more than you probably ever wanted to. If you don't have any aggregates in your index view, would you have this behavior? Is that your question? Not necessarily. You don't have to do this computation unless you have an aggregate. Yeah. Windowed computations are a broader form of aggregates. So we actually don't support windowed functions in index view definitions today, but just aggregates. Okay, so now let's update a view. This gets back to your question earlier. So if I have a view that's not materialized, I can actually do an update on that, and it will work. Well, how does it work? Well, the query processor goes and figures out what the original view definition was, and it tries to translate your original question against the view into an operation against a base table. So it does the translation for you and ends up building an equivalent query as if you had done update the original base table instead of updating the view. And it goes through and figures out whether or not you actually have all of these different pieces there. So it'll take the view definition and modify it, go back down to the base table, and then later it'll run the query for you. So let's look at the specific example. We create two tables, and I join them together, and I call it a view. And I actually have a where condition on one of them, and I have this with check option, which I'll get back to in a minute, but ignore it for now. I insert some rows into the base tables so that I can get some rows back, and then I update the view. So you'll look in the plan, and you'll see we do the join, which is in the view definition, and then we compute the new value, and then we do the update. So just as before, this is what all of our existing cases are: read, compute, update. And then we have this special stuff down here, which is this with check option. How many people know what with check option does? You guys have been sleeping with the ANSI spec, I see. The with check option logic is a special thing that says if you were going to update a view, and the update that you're performing against that view would cause the row that you're updating to no longer qualify the view, so it wouldn't come back if you were to do select start from view after that, disallow that change. So it's a special kind of constraint on views. And the way that you enforce it is almost identical to how we enforce foreign key constraints. So you'll see down here, we actually run a special version of the view again to see, does this thing qualify? And your question was, could we have avoided doing that earlier? And the answer is maybe. I haven't thought about it enough to say for sure, but we certainly don't do it now. And just like before, we have the assert at the end, so that if it comes back and it doesn't qualify anymore, we'll roll back that transaction and prevent that change from happening. Okay. We're getting close to the end. Oh, yes, question. Okay, so the question is, when you go and update views, there's restrictions about what kinds of statements are legal. And what are those restrictions? And have they changed recently? Is that a good summary of your question?
No. The question is still the limitation of that you cannot update columns that
Yes.
stays in two different tables.
Right.
It's still there, I just don't remember. And if yes, why?
So the question is there a restriction that you can't update a view where you modify columns that come from two source tables at the same time? And if so, why? So the answer is it is technically possible to build updates so that you could allow it to update a whole hierarchy if you wanted to. Historically, however, SQL Server has only done a single table because most people don't understand the full semantics of what it means to update a whole hierarchy in a single command. And there are some odd semantic cases that could be fixed but would require funny syntax or additional semantic clarification that most people have not asked for. So we restrict the update to actually go to one single table as a result, and that tends to simplify the problem greatly. Now, it hasn't changed in any recent release, but it is technically possible to go build a system that does more than that. I don't think that we've seen a compelling enough use case that makes us think that we should go and make that stronger yet, but that doesn't mean that we're uninterested in the subject. I've actually written an internal paper on exactly this topic about how we could do it one day if we ever wanted to. But it hasn't become the most important thing. So I think that you'll find that in many cases here, there's a balance between what is technically possible and what is commercially right to do. Okay, so table partitioning. How many people know what partitioning is? Okay, good. You guys are still awake. I'm happy. Partitioning is a feature that I helped build in the 2005 timeframe. It deals with splitting out tables so that you have a logical table at the top and multiple physical tables underneath. And what that does, it lets you do some really nice management structure problems whenever you have really, really big tables and you wanted to, say, move out old data. You don't have to do a big table scan of the whole thing. You can just swap out a chunk of the data in a very, very efficient operation. So that's really nice from a management standpoint. It also has some performance benefits in certain cases, although I don't think that's the primary reason people would deploy partitioning in my mind. So you want to be able to keep a window of, let's say, 3 years of sales data partitioned by day, and then you could swap out the old day every day and bring in a new day. So that would be a common windowing scenario you'd see. So in 2005, we had one set of plan shapes for partitioning, and in 2008, we actually changed it. So some of the things are visible in the 2005 query plan shapes in show plan that are not quite as visible in 2008. That doesn't mean you can't see them, you just have to look in different places. So in 2008, all the plans will look almost like they're non-partitioned. In 2005, there would always be an extra join with a constant table. And the constant table would iterate over the number of partitions. So if you had 10 partitions, you would have 10 rows in your constant table, and you'd say, give me all the rows from the first partition, and then give me all the rows from the second partition, etc. So that's still happening underneath the covers. It's just we didn't put it into an operator in the tree because we found that there were some things that we could do better if we pulled it out. Now, how on earth do we update a partition table or all the different tables physically that are underneath the covers? The good news is that it's a conceptual extension of what we've talked about before. We read the values, we compute the new values, we update the values. But the difference is you now have to think about not just what is the index key, but you also have to understand the partitioning key for each access method because they can be different. So you can have a clustered index that's partitioned one way, and you can have each secondary index partitioned another way. So the way that you should think about this is all the stuff we've done earlier, where you think, I need to understand the extra columns that get added in. Now there's just more extra columns. And the more extra columns help the system figure out what direction to go when it needs to go update a particular partition. Does it need to move to a new partition, or does it update the current partition? We actually do logic there. So let's talk about what that means. Now, when we're doing that split sort collapse, remember we had to figure out when we had key violations? Split sort collapse can also help you get things into the right order so that you scan them and do them in the order of the index. When you add partitioning, you also want to do it in the order of the partitions because switching partitions is a very expensive operation. It's like opening up a new table. To close down the old table, open up a new table, read ahead stops working. You have to do all sorts of things to get that to be fast. So you want to make sure you don't switch partitions all the time. It's much, much more expensive than just reading the next row. Split sort collapse will help us because we're going to include the partitioning keys And that'll make sure to sort all the rows in the order of the partitions in addition to the order of the indexes. And now we'll minimize the number of partition switching that we do. So there was a question before the talk on, can we do updates in parallel? And the technical restriction around that is actually interesting here. Partition tables do not support parallel updates, but because the storage engine for each table, physical table, does not support parallel updates. It could be fixed, but we have not done so yet. It's expensive to fix and it's hard to do technically, but it is possible. However, there's no restriction about doing partitions in parallel. So if you have one thread talking to one partition and another thread talking to another partition, that's just fine. Now, we do have a plan shape in 2005 that does this, but I don't know if it still works in 2008 or not since we changed to this new format. So if you guys are looking for a nice little advanced homework assignment, go figure out if you can create a plan that does per partition updates in parallel. I know you are all going to go off and skip the rest of your talks and work on it, but trust me, there are a few people here who will do it. Okay, so let's look at the partition example. So we create a partition function, we create a partition scheme. In this particular case, it's just we have a function that's really simple. We have boundaries on 10, 20, and 30. And then we insert a single row into this, and we say, let's just have the row value 1. And then we go run the query, update the partition table, set that column equal to 10 more, which is interesting because it means it needs to move from one partition to the next, right? So now our whole split sort collapse stuff means that split sort collapse means different things in partition tables because we have to delete from one partition and insert into another partition, whereas in the non-partition case, that would just be an update. Blew my mind the first time. You guys are lucky you're sitting down. Okay, so look, here we read, compute, and then we have to do split sort collapse. Even though this is a narrow plan, we still have to do split sort collapse in order to get this in the right order to avoid the phantom problem of deleting from the same partition twice or inserting in the wrong place. And as part of the partition logic, we add into split sort collapse. You'll see the compute scalar has an extra thing where it computes the new partition function, range partition new. So that's the partitioning function. And the boundaries are there. You can see them, 10, 20, 30. And it tries to figure out, well, what partition should this updated row go to? And once it knows that, it has the old value, and it was in partition 0, and the new value is in partition 1. And it includes that 1 and 0 in the split sort collapse computation, and then can use that to figure out, do I delete from partition 0 and insert into partition 1, which is the right answer in this case. So it's just an extension of what you learned earlier. Okay, I am done. You guys can ask questions now. Thank you. Yes, sir.
Is it correct to assume that you only do the split sort collapse as partition table or partition index updates, where the update has the potential to force a row to move between partitions?
So the question is, do we do split sort collapse when we don't have the potential of moving in partition tables? We can still have the problem of phantom primary key or unique key violation, and you can also have the reason to do it, that's performance. So sequential I/O versus random I/O. So those would be the three reasons why you could have it. Yeah. Other questions? Yes, sir.
When we do updates on read committed snapshot, it was introducing, at least in SQL 2005, it was introducing a word into the expanding the row, resulting in fragmentation and updates, so the tables become slower. Is that still a problem in updates with read committed snapshots?
So the question is, if you have GUIDs and read committed snapshot, does that make it so you don't have fragmentation?
No. The table doesn't have any row identifier or GUID before, but then when you do an update on a database that has read committed snapshot turned on, my understanding is it adds some row identifier column into the existing rows, which
Yes.
makes the row bigger.
Okay.
That leads into fragmentation.
So
Is that still a
the question is, read committed snapshot isolation has some special logic in the storage engine that adds a column, and does that cause fragmentation even with read committed snapshot isolation turned on? I believe that implementation is the same, although it's been tweaked and improved somewhat in more recent releases. I haven't done enough homework on that to give you a definitive answer, though, but if you come up, I'll give you my card, and I can follow up with you afterwards to make sure. I'll go talk to the guy that owns the storage engine. He was here yesterday, and we'll see. But I'm pretty sure that there's nothing new about that in 2008 R2 or 2008, and it still is an issue, but I think that it hasn't been a major issue to customers. I guess I'll phrase it that way. Should I use a heap or a clustered index as far as updates are concerned? You should use a clustered index in pretty much every case, independent of updates. And the reason is that heaps actually don't clean up space very well. So you separate from updates, you actually can have cases where you just have tons and tons of empty space in a heap, and a scan of a heap can become extremely expensive because it doesn't clean up the pages unless you rebuild the heap. So you actually want to use clustered indexes in almost every case, except perhaps temp tables. Yes? So if I have 3 indexes on my base table, are they updated in any particular order? The lock is taken on the clustered index when updating first, but that's the only statement we make about the order in which they happen. It doesn't matter what order they get done, right? We do have some heuristics to avoid deadlocks, but there's no guaranteed order about them. And frankly, it isn't an issue that we see regularly anyway. Yes? Yes. Yes. Okay. Excellent question. So when we do split sort collapse and we collapse things down and have an update for 2 to 2 in the example that we had earlier, do you actually do the update? Yes. And the answer is sometimes, but not all the time. So sometimes we'll just log the update and not write it. So we'll log something smaller. So there are some cases. When I was putting this presentation together, I tried to follow the instructions from the guys in the storage engine to make sure that I got one of those cases, and something wasn't working right on my internal build. So there are some cases, but I didn't have a release build on my machine to try, so I can't give you the exact cases, but typically there are cases where we are smart enough to realize that all we need to do when we're updating a row to itself in the storage engine is lock it, not log it or write it. But I haven't been able to reproduce the case, so I didn't show it today in the talk. So if you can reproduce the case, then log about it, because it's cool. Because then you don't have all the logging, right? Because that's obviously the big benefit. You don't have the logging on those cases. Well, you still would have potentially dirty pages in the pool for other rows that are being updated. But if you had a whole page of rows that weren't touched because you just updated them, then yes. Adam.
With regard to the unique fire, feel free to tell me to ask this tomorrow instead. I actually inserted 8 billion rows over a weekend one time. We're all listening to see if I was in error. I didn't get any error.
So I inserted 8 billion rows because because you had a good time for the weekend. And what?
I have no legs. So.
Right. Why didn't it have out of unifiers? And I need to look at your specific schema to say why. The case.
Table with a single column, create a clustered index, and links down.
So maybe there's something that I haven't seen. But the case that I have tomorrow is a very specific case around partitioning. So that's why I ran out of unifiers. But it's weird, so don't assume anything. I don't know why your case didn't have a problem with unifiers. Send me the schema, I'll take a look at it. So more questions? Yes, James. Can you tell what kind of spool it is going to memory, is it going to disk? I don't believe that show plan shows you enough information to see that. In the internal trees, we can kind of see that a little bit, but even then, it's never a binary thing, right? Oftentimes, the first chunk of it will be in memory, and then later it'll be not quite as in memory, and it changes from one release to the next because we keep improving it. So, no. But should we make it more visible? Probably we should do a better job on that. If you have use cases where you wanted to know whether it's spilled or not, or you needed to know what kind of spool it was, independent of whether it actually spooled or not, I would love to see it, so send me a mail with that. Yes?
Simple question. How does the query optimizer, how does it decide if I have 3 different indexes all with, let's say the first index is covering this column, second covers the same column plus 1, and the
So if you have cases of overlapping indexes, so they have some columns that are the same, how does the optimizer know which one to pick? The basic answer is that it picks the one, it has a heuristic, and it depends a little bit on which case you're in, but overall, the general heuristic is based on row width, how many bytes each row takes, time, well, basically how many pages it is. So the one with fewer pages is more likely to be picked because it'll be cheaper to scan.
Well, that's not always going to be the case, though, necessarily. Okay.
But as a general rule, the problem is that that's a very local statement about that portion of the plan. It may be that a wider index is actually better for a broader set of operators. So if you have to do a seek of a very narrow index and then fetches for every single row, that's random IOs again. Versus an index that's a little bit wider that you can scan, well, there's a trade-off there, just like any other seek scan trade-off. Okay, other questions? James.
With the halloween protection and the space separation, if you're talking about one row update, it comes in on the first iteration, and then you get a plan cache, and then someone uses it. Will it only put that screen, take the school out, guarantee on every occasion without the one row update? It's always going to be a one row update.
So the question is about one row updates. And I didn't cover this in depth in the talk, but I told you there was special logic. We do all sorts of bending over backwards to try to not put that spool in. If the optimizer can determine that a particular update will only ever affect one row, then it can sometimes avoid the spool because it means it would never read a second row and therefore couldn't see itself more than once. So how does it do that, and can it figure out whether or not, can that plan get cached and then used in a case when there is more than one row? The basic answer is we do semantic analysis on the tree and determine whether or not, in all cases, that query can only ever touch one row. And that's the case we do the one-row update optimizations. And that's the only cases we do the one-row update optimization. So we wouldn't be able to do it unless we can prove that it only ever touches one row. And if we have a cache, like if we have another, the query itself, there has to be a different query text, and therefore a different cache entry for that to not be true.
In the SQL internals book, it says that query optimizer will not look through all plans to decide how best to solve the query, but it will look through an appropriate amount of plans to solve that. How does that work?
Okay, so this is a broader question about the optimizer, not just updates.
Right.
The question is, in the book, which I assume...
It's in, I think, both internals books.
Okay.
2005 and 08.
So the optimizer has a dynamic search algorithm for how it picks a query plan. In updates, it actually rarely matters that much except for the select portion, the read portion of the query plan, because most update plans are actually determined by your schema choice, not because there's a bunch of different things to search. There's a few choices, but so small that it's not a huge search problem. In select queries, especially when you have lots and lots of joins, it's technically impossible to search the whole space. So the dynamic search algorithm will try to seed a search structure with an initial set of plans that it thinks are good, and then it'll try various algebraic rewrites against those, and it'll continually cost those to figure out, is it getting a better plan or not? And it gets to a point where it says, well, I've been searching for a certain amount of time, and I found a plan that costs 23. And it's not worth spending more time because my odds of finding a plan that costs 10 aren't that high if I'm going to spend another 15 seconds searching. So there's a balance there between time to search the space and quality of the plan found so far. And that's a dynamic programming problem. It's similar to how a chess program would work. So it tries to search for a while, and the longer you have, the more moves you can consider. And that's basically how the optimizer searches the plan space. It's more of an issue in selects than in updates. Yes, sir.
Connor, the wide plans you were speaking about fairly early on, if I understood you correctly, the index update becomes batched, if you like. So within the transaction, it decides this is a wide plan, and I'll update the index at the end and sort of rewrite it or whatever it does. Presumably, that takes an extended or protracted amount of time. Is that one of the reasons why SQL Server at times the optimizer ignores indexes?
Say that again. I didn't quite follow you. I apologize.
Wide plan?
Yes.
When the batched update of the index happens,
Yes.
it takes a long time.
Yes.
Is that, well, relatively speaking, but is that one of the reasons why the optimizer at times will ignore an index on a table and it'll just do a table scan?
So the question is, Wide updates are relatively expensive compared to narrow updates because there's more overhead associated with those spools and those sorts, and the fact that it's sorting each one, so it has a latency issue because it's not updating all the indexes at the same time. Does that mean that in regular select queries it'll ignore indexes sometimes? Is that, no, those are unrelated. It might be that you have longer time to wait for an update query to complete, and therefore your select query might block, but it doesn't affect the plan choice for select queries. The plan choice for select queries is largely independent of what's happening with locks and updates. The optimizer doesn't know about locks, really. It doesn't care. And so it just generates plans absent the heuristics I described in the talk, and that's all it does. So it'll still make cost-based decisions based on just what's the size of that index and what things are being touched and what's the relative proportion of the rows that'll be returned according to the statistics. So it's more of a general costing question rather than anything specific with updates.
So there's not a statistic that says we are doing too many of these wide plan updates to an index, so don't use it.
So you have actually a very, very profound question. So could the optimizer be smart and understand the workload and make some choices about what kinds of updates to do, wide versus narrow, or whether or not to bother keeping an index around based on its update versus select ratio? And the answer is yes, we could eventually do that. And I hope one day we can.
Well, you hope one day we can, so that's not happening yet.
No, not in any public release that I can tell you about. Yes, sir.
Are there any optimizations done internally whenever you are updating a large set of rows versus a small set for a table? Say you're updating your entire table, do you do anything internally to make that happen?
So the question is, are there different optimizations that happen for doing a large set of up changes versus a small set of changes? Well, wide updates and narrow updates are one, and then bulk operations would be another. Partition switching would be a third. Truncate table would be a fourth. So they are all things that you probably are familiar with. There are other things that we do about how do we allocate memory and how do we batch things that are purely internal. And they don't really make any sense to describe here because they're just too physical. But overall, yes, we try very hard to be faster on things when there's a lot of them. And I think what you're going to find from an industry trend standpoint is as soon as you start doing a lot of something, it becomes very valuable to figure out how to optimize that something. The column index presentation that Susan Price will be doing later this afternoon is an example of one of the areas where in the data warehouse space for a subset of the queries in our algebra, we can do things a lot faster because we can take those specific kinds of queries and run them much more quickly with a specific kind of indexing structure. So you might want to go there, and that'll give you another sense of what kinds of things we do faster in bulk, maybe. More questions?
Yep.
Yes?
Does the query optimizer have different costs for random IOs? For example, if you're doing getting solid state disk?
The question is, does the costing change based on your storage subsystem, for example, solid state disks, SSDs? The answer right now is no. We do not change that. We didn't, when we did SQL 7, we made a conscious choice that we didn't want plan problems to only reproduce on the specific physical machine. So we made a general model that was representative of the cases at the time. Now, since then, of course, the array of storage subsystems that are available to you are much, much larger with much bigger performance deltas. And over time, we might actually provide a better sense of, I have very, very fast random IOs on my particular storage subsystem. Or I'm a SAN and I have certain things which are extremely fast, other things that are high latency. And I think we don't have anything in the current release product that was announced today that does that, but it's an area that we've looked at and we will continue to look at. So for now, if you have a plan that gets picked that happens to be faster if you picked a different plan, we see that occasionally, maybe once or twice a year, but not too frequently. And you can use a query hint if you wanted to force a scan or a seek plan instead of the opposite. That would be the solution right now. But we see it so rarely that it hasn't been a major issue for us.
Your construct wouldn't change that, would it, though, that regardless of what that physical storage looks like, whether it's a SAN or it's a spindle, whatever that is, you don't care. You can still say that we don't want to have to go to disk. Obviously, if we already have it in a buffer, I mean, yeah, it might be faster because it's solid state now, but you don't have to make
so the question is, it isn't a question of what physical storage it is. It's the properties of the storage and the relative costs of those. Right. So the tipping point between seeks and scans would be different on SSD drives. So you would have a different point where you'd want to be able to pick one plan or next being optimal. Or how accurately you represent the real physical model with your logical costing model is sort of the broader question. And there are cases where it can get a little bit out of whack today because people find extremely fast storage subsystems. But I won't say that it's the common case. It is more of a high-end problem than a regular problem. You'd have to really be trying to hit that case. But there are people who have very high-end systems these days, and it's an area where in the future maybe we'll do a feature to help make that better for those tier 1 customers. Yes, sir.
Do you plan to ever do per partition statistics?
Per partition statistics, should we do them? Yes, we should do them. Have we done them yet? No. Hopefully soon. Sorry, we don't have them yet. I wish we did.
I was going to do it the other day. I don't know.
No, we don't have them yet. Other questions? Yes.
You have a composable DML statement. Target that you may want to discover the subset. There's a distinction that the target cannot be a part of the correctly constraint.
Yes.
Is that the optimizer restriction or
So there's a feature that we have which is insert with outputs. So the with outputs feature that I mentioned to you guys earlier has the ability to take the output of an update or an insert and then insert that into another temp table, a table variable or something. I can't remember the exact restriction. So that table is one of these examples where you can chain together updates for different target tables. And there are some restrictions on these that are largely just testing and simplicity restrictions at this point. There certainly are things we can do in that space, and we've done enough to do benchmarks, basically, that could use it. We haven't done enough to capture every single user scenario, and in the future, hopefully, we will. I think you'll find that the market is a very interesting place right now. There's a lot of stuff happening. These are primarily OLTP scenarios where you're trying to avoid round trips for multiple small queries by batching them into one larger query. There are lots of things that are interesting in that space, and over time, I think we will improve that space either programmatically or otherwise. So I don't know what order we'll get to all those things, but we are interested in the space for sure. Okay, guys, thank you very much. I appreciate it.